what exactly is it? Super simple, really. The Haber process is just the industrial way we make ammonia. That's the whole goal. You take nitrogen gas, you take hydrogen gas, you combine them, and boom, you get ammonia. And that ammonia, well, it's the absolute foundation for almost all modern fertilizer.
Okay, but to really get why this thing is so clever, we've got to get nerdy. We need to zoom way in and look at the actual chemical blueprint. Let's see what's happening molecule to molecule.
Okay, here it is, the recipe. You take one nitrogen molecule, mix it with 3 hydrogen molecules, and you get 2 molecules of ammonia. Simple enough. But look at those arrows in the middle. See how they point both ways? That's super important. It means the reaction is reversible. The ammonia can actually break back down into nitrogen and hydrogen. And the other big thing, it's exothermic. All that means is when you make ammonia, it gives off heat. So remember those 2 things. It's reversible and it releases heat. They are the key to this whole puzzle.
All right, so where do we get our ingredients? Well, nitrogen's the easy one. The air all around us, it's about 78% nitrogen. We just take it out of the air. Done. Hydrogen, on the other hand, that's a bit more work. We actually have to make it. And the most common way is by reacting natural gas, methane, with steam. So one's free and easy, the other we have to cook up ourselves.
And you can see that difference right here. On one side, you've got nitrogen, just being pulled from the atmosphere. Easy peasy. On the other side, well, that's the whole industrial setup you need to produce hydrogen from natural gas. Totally different ballgame for each ingredient.
Okay, so we've got our ingredients, we've got our chemical recipe. Now for the big question. How do you take this from a chemistry textbook and turn it into a gigantic worldwide industry? Let's go inside the machine and find out.
So here it is, the whole shebang. Now the first thing you'll probably notice is that everything is going in a circle. This is not a one-and-done kind of deal. It's a continuous closed-loop system, and it's all designed to be as efficient as possible. So come on, let's follow the path of the molecules and see how it works. All right, here we go. First up, the nitrogen and hydrogen gases are piped into the system. Then comes the main event. These gases get squeezed hard. We're talking 200 times normal atmospheric pressure. Then they're heated up to a toasty 450 degrees Celsius and passed over a bed of iron pellets. That's our catalyst. Now for the really clever bit, step 3. The mix of gases comes out and gets cooled way down. Because ammonia turns into a liquid at a higher temperature than the other two, it condenses out first, so you can just drain it off. But what about the leftovers? The unreacted nitrogen and hydrogen? And this is the genius part. You don't just vent them into the air. Nope. You send them right back to the beginning of the line to go through the whole process again. Nothing is wasted.
Okay, now we're getting to the real brainy part of this whole thing. This is the massive puzzle that the chemists Fritz Haber and Carl Bosch had to figure out. I like to call it the Great Compromise.
I mean, think about it. Why those numbers? 450 degrees Celsius, 200 atmospheres of pressure. They feel so specific, right? They're not just random numbers pulled out of a hat. They are the result of this incredible balancing act between getting what you want chemically and what's actually possible and affordable in the real world. So here's the problem they faced. It's like a 3-way tug of war. If your only goal is to get the most ammonia possible, the highest yield, you'd want a low temperature and super high pressure. But if your goal is to make it happen fast, a high reaction rate, you need a high temperature. And then there's the money and safety side of things. To keep costs down and prevent explosions, you want a low temperature and low pressure. See the problem? These goals are all fighting each other.
Let's break down the temperature first. Remember how we said the reaction is exothermic? It gives off heat? Well, chemistry tells us that for reactions like this, you'll get the highest yield at low temperatures. Awesome. Except at low temperatures, the reaction is so ridiculously slow, it's useless. So they had to find a middle ground. 450 degrees Celsius. It's hot enough to make the reaction happen at a practical speed, but it's still cool enough that you get a reasonable amount of ammonia.
Now, what about pressure? With pressure, the chemistry is easier. The higher, the better, period. More pressure squishes the gas molecules together so they react faster. It also pushes the reaction towards the side with fewer molecules, which in this case is the ammonia. So great, let's crank it up to 1,000 atmospheres, right? Well, no. Trying to build and operate a factory that can safely contain that kind of pressure is just insanely expensive and incredibly dangerous. So again, it's a compromise. 200 atmospheres is high enough to get a good yield and a fast rate, but not so high that you're breaking the bank or, risking a catastrophic failure.
But there's one more trick up their sleeve, the catalyst. A catalyst is like a chemical shortcut.
It's a substance that you add that makes the reaction happen way faster, but it doesn't actually get used up itself. It just provides a helpful surface for everything to happen on.
And this is maybe the most important thing to understand about the catalyst in this process. The iron, it does not make more ammonia. Let me say that again. It does not increase your yield one bit. Its only job is to be the gas pedal. It makes the reaction go faster. That's it. Without the iron catalyst, even at that compromised temperature of 450 degrees, the whole thing would still be too slow to be useful.
So you hear all this talk about compromises, not the best temperature, not the best pressure, and you might be thinking, wow, this process doesn't sound very efficient at all. And that brings us to the final and most brilliant part of the whole system.
Because after all that engineering and balancing, get this, on any single trip through that hot, high-pressure reactor, only about 15% of the nitrogen and hydrogen actually becomes ammonia. Just 15%. That sounds terrible, right?
So that's the big question, isn't it? If your yield is so low on each pass, how can this possibly be an efficient, world-changing industrial process? How does that work?
And here's the secret sauce: recycling. It's that simple and that brilliant. You pull out that 15% that turned into liquid ammonia, but the other 85% of gas that didn't react, you just loop it right back around to the beginning to take another trip through the reactor, and again and again. By never throwing anything away, you eventually convert pretty much 100% of your starting ingredients into the final product. The yield per pass is low, but the overall yield is nearly perfect. It's just genius.
So let's just recap. You've got your temperature, a perfect compromise between speed and how much you make. You've got your pressure, a balance between getting a good result and not breaking the bank. You've got your catalyst, which is just the turbo button. And finally, that amazing recycling loop that makes the whole thing incredibly efficient in the end. It's this whole system of compromises all working together in perfect harmony.